there's two basic kinds of statistical inference. One is where you know the standard deviation of the population.
Mm-hmm.
If you know, let's just write it. I can understand why I went 7 years and nobody requested tutoring in statistics. It's a hard subject to tutor. If the standard deviation is known, then you're going to use the Z test or measurement or whatever word they use. If you
Mm-hmm.
have an unknown standard deviation, which is the case with most things,
You'll end up using T.
exactly, with number of degrees of freedom. And
Mm-hmm.
if you're like me, this was like Greek first time through it. I had no idea what they're talking about with this number of degrees of freedom. However, second time through it, I started grasping it a little bit better. And the one thing I know is that if you take a typical normal distribution
Mm-hmm.
and you compare it with distributions with various degrees of freedom, in other words, if I said 3 degrees of freedom, it's going to have more area in the tails.
Mm-hmm.
So it's going to look more like that, which to me says a higher standard deviation also.
Mm-hmm.
Because remember, standard deviation has to do with the area under that curve. And when it's a high middle and low tails, you got a lot of area that's within 1 or 2 standard deviations. Whereas if you have a lot of area under the tails, then the standard deviation almost has to be greater out of necessity. But if I wanted to graph T of 19 degrees of freedom, then I'm going to get something that looks a lot closer to my normal distribution.
Mm-hmm.
So as the number of degrees of freedom increases towards infinity, then the graph basically becomes the same as a normal distribution.
Mm-hmm.
Now, let's just talk about a little bit different. The standard, when I say the standard deviation is known, that's of the total population.
Mm-hmm.
So let's just take a couple of examples. If we're talking about the, what would be a good thing that we would know? Let's say the average age of everybody in the United States. Okay?
Okay.
In other words, we actually have census data on that. So we don't have to get that from a SRS, a standard random sample. We know what the mean, we know what mu is, and we know what standard deviation is for the average age of people in the United States. When we know that, then we're looking at, let's say somebody said, well, what is the average age? If you did a sampling of 1,000 people and you wanted to know what the likelihood of your mean being within the confidence interval. Have you gotten the confidence intervals and stuff?
Mm-hmm.
Okay. Then you're going to use the known mean and standard deviation of the total population in order to deal with your SRS. Let me just put it at that. And there's equations that I could look up in the book, and we could write them down, and we could actually do some example problems. And that's really where we need to get to, is where we need to go through one of these problems and apply these formulas. Now, so far, the only thing I've done is read all the examples in the book, which are pretty instructive, but you don't really learn it until you actually do one on your own, and I haven't really done much of that. So that's why I'm hoping you'll send me some so that we can either do them together, or I can at least look at them in advance and see if I can find an example problem to do and then figure out how to do that problem.
Okay.
Now, here's what I understand. You use the Z. In fact, I think you use Z, I don't remember what the rest of it is. I think it's times standard deviation all over the square root of your sample. That is the key formula involved when you have a known mean and standard deviation from the total population. But that's rare. Usually you don't know what it is. And so if I do a standard random sample on 1,000 people, and I want to figure out how does this sample relate to my population. In other words, let's say I don't have a Census Bureau that collects this data, so I really don't know what mu is or sigma, but I just do 1,000 sample. Well, that sample, that 1,000 sample is going to have its own mean, and it's going to have its own standard deviation. They're not necessarily going to be mu and sigma. They're going to be whatever the mean of that 1,000 people is and whatever the standard deviation is. In other words, if we do a sample of 1,000 people and just measure the age of everybody, we can certainly come up with what the mean is, and we can come up with the standard deviation.
I found some examples on her website and sent them to you.
Okay, if I'm going to use this, then that's where I use the T instead of the Z. In other words, if I have an unknown population standard deviation, I don't know what sigma. You know what the difference is here when I write mu and sigma as opposed to X bar and S?
Sample and population.
Yeah, this is the known mean for the entire population. Sometimes you do know that, and you also know the known standard deviation of the entire population. Other times you don't know that, and you're taking a sample trying to figure out what the best way to infer what those two numbers are. Well, what you start with is the mean of your sample and the standard deviation of your sample. Let me go to my let's see. Do I want to click on that link or
Let's click on the PDF.
The PDF? Okay. Okay. Yeah, so she is definitely going in the same direction. Better yet, This is perfect, Cole. Thank you. Because these are examples from the book. I don't think she's changed anything. Hold on, let me look it up. Nah, hold on a second. I went back too far. This is chapter 10. Okay. There's definitely a question on tension on fine wires. In fact, the most interesting thing I have discovered about statistics is all of these cool things, all these cool relationships. Like, you probably haven't seen them all because you don't use the same textbook. But yeah, I have this problem in my textbook, and it is a duplicate of what she has on here.
Okay.
So we could definitely go through this. I know how to go through these examples. That's one thing I do know how to do.
Okay.
And I'm not sure that I can do a fresh problem on my own, but I have gone through, up to this point, each of these pages twice, so I certainly can follow their examples.
Okay.
This is perfect that she's using the examples from the book. All right, so let's figure out how to do this. We have probably just enough time to go through this whole thing. Got a few of them. Okay. Let's see if her example 3 is on my book. No, I don't think that one is. But that's a good thing. That means it gives us a chance to do problems that are fresh and that I haven't seen yet. Wow. If you could send me something like this before our sessions, it would be so helpful.
Okay, I'll try and remember next time.
Okay. I think I can tell enough about this that notice the key is the known sigma. That's our type 1. That means we're going to use the Z formula. Here, let me blow this up a little bit. Take a screenshot. Limited by time today. I do have a 6 o'clock. But that, hold on. Notice the key formula is a Z formula, not a T. You use the T when you have an unknown sigma. Or you use the T when the best sigma you have is from your sample. This sigma is from the entire population. Careful study has shown that when you know all the data, sigma is that. And so what they did was take an SRS of 20 screens, and they want to find out information based on their sample. So the question is, construct a 90% confidence interval for the mean tension of all the screens produced that day based on this sample of 20 screens and a known sigma. Notice that we don't even have to know what the mu is. We don't have to know what the mean is, because all we need to know is sigma. Okay, so identify the population. It's the mean tension in millivolts of all TV sets made by that manufacturer. Verify the conditions. It's an SRS. Yes, it is. We're randomly selecting 20 screens. Normality. It's not stated, but as long as n is less than or equal to 10, the critical limit theorem applies, or excuse me, does not apply if it's less than 30. Hold on a second. Let me see what that has to say here. Normality is sampling approximately normal. Past experience suggests that they do follow a normal distribution. But what if the population distribution weren't known to be normal? The sample size is too small to use the central limit theorem. The central limit theorem basically says this, that if the population is greater than, I think, 30 times the sample, then even if the population is not normally distributed, our samples will be. If we were to take numerous samples. In other words, at least that's the way I understand it. Let me see if you agree. In other words, let's say that the mean tension levels, if we were to examine every single TV set from this manufacturer, was not a normal distribution. Let's just say that. Let's say it came out to be slightly different than a normal distribution. Skewed one way or the other. You know what I'm saying? If you don't, I can graph it. In other words, normal distribution, there's a skewed distribution. This is not normal. That's normal. Well, what the central limit theorem says is that if your population is not normal, but you do repeated samples, and you measure the mean of those repeated samples, that will be normal. You will have a normal distribution. At least that's my understanding of it. I'm pretty sure I'm right there. And that's the central limit theorem in a nutshell. Now, the reason we can't apply the central limit theorem here is because n is less than 30. And I'm not sure exactly what the limitations are on the central limit theorem, but n has to be sufficient, and the population has to be sufficient, and the ratio has to be sufficient to apply the central limit theorem. And in this test, it's not applicable, but when you look at a box and whiskers plot, right? That's what this is, box plot. It looks fairly normal. In other words, I don't have big extremes. It doesn't appear that I have very many outliers on that thing. And the box plot is fairly normal. There's no outliers. And so it's safe to assume normality. Independence. The TVs should be independent from each other, and they are. And the population is estimated to be greater than 200 TVs, which is greater than 10 times n, our sample size. And I do know that that is n greater than 10 is definitely, or excuse me, population needs to be 10 times n. So, given check mark on 1, 2, A, B, and C, then we can use the Z process to figure out normality, or rather the margin of error and the confidence interval. Now, E is the margin of error, which is Z times the known standard deviation. Hold on, excuse me. Unfortunately, yeah, no, we still got 10 minutes. That's the key formula. Dealing with a known sigma is the Z value times the known sigma divided by the square root of the number of samples. Well, we know all of that. We know sigma. We know that. Where'd we get that? We got that by going to the Z table, at least if you're doing it my way, as opposed to your calculator. This is something I have not mastered at all, and that is how to use the inspire in these. And I can tell that I really need to figure that out. That's going to be everything with statistics, is using the calculator is my guess. How do you get this step? This step where it gives you the Z value, I know how to get it out of the table. I go and I find let's see, a 90% confidence interval means that you have 5% to the right, 5% to the left. So basically, you're looking for a Z value where 95% of the area lies to the left.
What you do is you take you go into statistics and then functions. So menu, statistics, functions, and then go down to inverse norm.
What do I have to have in there? Do I have to have anything pre-entered like this table of values?
No, you just need to go to your scratch pad.
Well, let me do it, if you don't mind.
No, not at all.
I'm going to do it as you help me. I don't like the scratch pad that's a document. I prefer my scratch pad. But anyway, I'm in the document. So what do I do?
Okay, so hit menu.
Okay.
Then go to statistics.
Okay.
Then go to functions.
Which must be lower than 7. I don't have functions on mine. I got stat calc, stat results, list math, list operations, distributions, confidence interval.
Distributions. I'm sorry, distributions.
Okay. And now what?
And then go to inverse norm.
Okay. And this is for my Z table. Okay.
Yeah. So
here I'm going to type in is going to be 95?
No. So then you would put the percentage that you want to the left.
That's 95.
No, so you want 0.05.
Oh.
So you want everything to the left of what you want. It will give you.
Okay. That's kind of the opposite of the way this book has taught it to me. A Z
That's just the way the calculator
is to the left of that Z value. But I'll do it your way. You know more what you're talking about here.
It'll give you a negative. It will give you the negative version.
Okay. See, I could put 0.9. If I put 0.95 in there, I'll get the same Z value, only positive.
Yep.
Why?
Yeah. Yeah, you will.
Okay. So if I hit enter, it gives me minus 1.64. Yeah. Let's just talk about that for a second, because I think there's...
Your calculator might have a float. You may not have as many float digits.
Well, oh, really? Okay.
Yeah, you can change the float digits.
What I'm looking for. I'm looking for this, where 90% of the curve is under that. Okay? That means 5% is there and 5% is there. Well, if I go to a z table, everything to the left of that point is 95%. So if I go to this table you just gave me and put in 95%, then I get that right there. And that's a positive z number. Now, you did a negative z number, which gives you 5%, which is going to give you basically the same amount, although you don't want to put the negative z value in there. You want to put the positive one, because we're looking at 90% confidence interval. So, okay, so that gives us our margin of error. And we were able to calculate our mean from our sample of 20 intervals. So our mean is going to be that plus or minus our margin of error, which gives us that, which tells us interpret your results. I'm 90% confident that the true, and this is a little tricky here. This is not quite the same as what I thought it was when I first read it. I'm 90% confident that the actual mean, mu, of all the TVs is in this interval between 290 and 322. What it does not say is what? I had this understood at one point. I'm not sure I do now. There's another interpretation of that one could make that isn't actually correct. And I think that is that there's a 90% probability that the mean that I calculate, and I can't think of the one that isn't quite true. I'd have to go through my book again. But it's important to word it this way, that you're 90% confident that the true mean, which is mu, is in that interval. Construct a 99% confidence interval. Okay, so you're going to put in, the way you did it, you would put in 0.05, correct? No, 0.005.
If you're doing 99%, yeah.
Yeah. Or the way I would do it, I would put in 99.5 to get the positive z value, and that's 2.576, which gives us notice, a bigger interval. Well, that makes sense. If we're 90% confident that the true mean lies in that tight interval, well, then it makes sense to be more confident that the true mean lies in a broader interval. Notice this interval is 9 points further left and 9 points higher. So this is definitely a broader interval. The more broad the interval, obviously, the higher confidence you're going to have that mu lies in that interval.
Just, it's 6 o'clock.
Okay. Perfect.
I just know you said you had a session at 6. So
thank you very much. Yes. And this was very helpful. This is exactly what I'm looking for.
Right. I'll try and remember to send you something earlier.
Thank you, Cole. Talk to you next time.
Talk to you next time.